a quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in. Let the outside world dissolve and gently descend into tonight's world. For decades, the idea of a multiverse has lived on the edge between science and science fiction. In this episode, we lay out what people mean when they say many universes, why some modern theories point in that direction, and where the evidence stops. We will look at the main versions of the multiverse, the arguments for them, and the strongest reasons to doubt them. The goal is not to convince you, but to make the ideas clear enough that you can judge them yourself. Tonight, we examine the multiverse theory. Imagine you are standing in a huge library at night. The lights are low, the air is quiet. You are holding one book, open to one page. You can read only that page at this moment. Now imagine someone tells you something strange. They say the library does not contain one copy of the book. It contains many copies. In one copy, the next page has a different sentence. In another copy, a character makes a different choice. In another, an entire chapter never happens. And the copies go on and on, stacked in rooms you cannot reach. That library picture is not science, but it is a useful way to start, because the multiverse idea begins with a very human feeling. We look at the universe and we ask, why is it this way and not another way? We notice that some numbers in physics seem oddly specific. We notice that quantum events look random. We notice that the universe is enormous and we can only see part of it. And we start to wonder if what we call the universe might be just one region in a much bigger reality. Tonight, we will keep our feet on the ground. We will use plain language. We will use careful analogies. And we will separate three things that often get mixed together. First, we have the universe we can observe. That means everything we can, in principle, see or measure with light, particles, and telescopes, given enough time and technology. Second, we have the universe beyond what we can currently observe. This is still the same universe, but it may include regions so far away that their light has not had time to reach us. Think of it like being in a foggy field with a flashlight. The darkness beyond your beam does not mean nothing exists there. It only means you cannot see it. Third, we have the stronger multiverse idea. This is the claim that there are other universes that are not just far away. They may be separated by a barrier we cannot cross. They may have different laws of physics. They may come from different outcomes of quantum events. They may not share the same space and time as we do. When people say multiverse, they can mean any of these. So we will build a simple map. One kind of multiverse is the easiest to picture. It says the universe is much larger than what we can observe. Maybe it is infinite. If it is infinite, then the number of possible arrangements of matter in a region the size of our observable universe is very large. But it is still not infinite. That means, in an infinite universe, patterns would repeat. Far enough away, there could be a region that looks almost exactly like ours. Not because of magic, but because of basic probability. A second kind comes from a theory about the early universe called inflation. Inflation is the idea that, for a tiny fraction of a second after the universe began, space expanded extremely fast, faster than normal expansion. If inflation happened, it can explain why the universe looks so smooth and flat when we look at it on very large scales. But some versions of inflation also suggest that inflation might not have stopped everywhere at once. it might keep happening in some places. If so, then bubble universes could form. Each bubble would be like a separate, expanding universe. A third kind comes from quantum mechanics. This is the idea that when a quantum event has multiple possible outcomes, all outcomes happen, but in different branches. This is often called the many worlds interpretation. It can sound like science fiction, but it was proposed by serious physicists as a way to avoid a fuzzy idea called collapse. In many worlds, the wave function never collapses. It just keeps evolving, and the universe splits into branches where different outcomes are real. A fourth kind is often connected to string theory. String theory is a speculative framework that tries to unify gravity with quantum mechanics. It suggests that the deep structure of reality could allow an enormous number of possible vacuum states, which is a fancy way of saying an enormous number of possible ways the laws of physics could settle. This is sometimes called the string landscape. If inflation creates many bubble universes, and if each bubble can land in a different vacuum state, then you might get a multiverse with many different physical laws. That is the menu. But before we go deeper, we need a simple rule. A theory is not automatically good because it is complicated. A theory is useful when it helps us explain observations and make predictions. If a theory explains everything by allowing anything, it can become impossible to test. That is one of the biggest problems with multiverse ideas. They can be hard to pin down. So we will ask the same questions again and again. What is the idea trying to explain? What does it predict? What could prove it wrong? And what are the strongest reasons to be cautious? To stay in layman's terms, we will treat physics like a set of rules in a game. Imagine you are playing a video game. The rules of the game decide what can happen. Gravity has a strength. Particles have masses. Some forces attract, some repel. The game can still have randomness, like a dice roll, but the dice only roll within the rules. In our universe, the rules are the laws of physics and the constants we measure. We do not fully know why those constants have the values they do. We can measure them. We can build theories that connect some of them, but many values still look like inputs. Here is a simple example. If the strength of the electromagnetic force was slightly different, chemistry would change. Atoms might not form stable molecules the same way. Life as we know it could become impossible. Now, careful. This does not mean the universe was designed for life. It only means life depends on certain conditions. It is like saying fish depend on water. That does not prove someone built the ocean for fish. Still, the question is real. Why do we live in a universe with a set of rules that allows complex structures, stars, planets, and life? One answer is that there is only one universe, and the rules are what they are. Maybe a deeper theory will one day show that they could not have been different. Another answer is that there are many universes with different rules. We observe this one because only this kind allows observers like us. This is called anthropic reasoning. It is not a magic trick. It is a selection effect. It is like a person waking up in a hospital and saying, "This building must be designed for breathing." No, they are in the one building where breathing is supported. Anthropic reasoning can be used carefully, but it can also be used to stop thinking. It can become a way to explain any number by saying, well, if it was different, we would not be here. That is true, but it is not always satisfying. So the multiverse debate often becomes a debate about what counts as a scientific explanation. Now we can begin with the first and simplest version. Suppose space continues beyond what we can see. This is not controversial. We already know we cannot see everything. Light has a finite speed. The universe has a finite age. So there is a horizon, like the edge of your flashlight beam in the fog. If the universe is infinite, then there could be infinite matter arranged in infinite ways. But to keep it simple, imagine just a huge but finite region, much larger than what we can see. In that case, other regions could have different histories, different planets, different stars, different people. If the region is large enough, you might even get a region with a copy of Earth. Not a perfect copy, but extremely close. This kind of idea is weird, but it is weird in a normal way. It is the weirdness of large numbers. If you shuffle a deck of cards, you almost certainly get an order that has never existed before in history. The number of possible deck orders is enormous. But if you had a machine that could shuffle decks forever, you would eventually repeat an order. It is not because the machine is special. It is because the space of possibilities is large, but not infinite. In an infinite universe, the deck shuffle machine runs forever. So far, this is not the dramatic multiverse people argue about. This is just a big universe. The problem is that it may be impossible to test directly. If a copy of Earth exists so far away that its light will never reach us, then it is not an observable claim. It might be true, but it sits outside normal evidence. Still, it can be connected to evidence indirectly. If measurements of the universe suggest it is flat and continues without end, that supports the possibility of infinite space. If we measure the geometry of space and it is extremely close to flat, that is one hint. But it is hard to prove true infinity with finite measurements. So we move to inflation, because inflation was invented to explain real observations. To explain inflation without heavy math, picture a balloon with dots drawn on it. The dots are galaxies. As the balloon inflates, every dot moves away from every other dot. That is like cosmic expansion. Now imagine that, for a tiny moment, the balloon inflates insanely fast. So fast that parts of the balloon that were once close are suddenly far apart. This can smooth out wrinkles. It can make the surface look flat on small scales. It can also spread out energy and matter in a way that matches what we see. Inflation is still being tested, but it has strong support because it fits the patterns in the cosmic microwave background, the faint afterglow of the early universe. Here is the key point. In some models, inflation is not a one-time event that stops everywhere. It can be like boiling water. Imagine a pot of water heating on a stove. Most of the water is calm, but in some places, bubbles form. Each bubble is a separate region where the water is doing something different. In eternal inflation, bubbles of normal, slower expansion form inside a larger inflating space. Each bubble becomes a universe like ours. The space between bubbles keeps inflating, so bubbles get pushed apart faster than they can reach each other. That gives you a multiverse of bubble universes. This is where things start to feel both exciting and frustrating. Exciting because it could explain why our universe has the properties it does. Frustrating because other bubbles might be causally cut off from us forever. Some physicists argue that we might still find indirect signs. For example, if another bubble collided with ours in the early universe, it could leave a pattern in the cosmic microwave background. People have looked for such patterns. So far, there is no clear evidence. So inflationary multiverse ideas live in a middle zone. They are motivated by a successful theory. They may have testable consequences, but the strongest claims are hard to confirm. Now we come to the quantum multiverse, many worlds. To make this understandable, start with a simple fact. In quantum mechanics, the world is described by a wave function. The wave function is not a wave in water. It is a mathematical object that tells you the probabilities of different outcomes. When you measure a quantum system, you get one result. For example, an electron can be found in one place or another. The wave function can describe both possibilities at once as a superposition. But then you measure and you see one outcome. The usual story says the wave function collapses. One outcome becomes real and the other disappears. The problem is that collapse is not part of the core equations of quantum mechanics. The core equations are smooth and deterministic. Collapse looks like an extra rule added on top. Many worlds tries to remove the extra rule. It says, there is no collapse. The wave function always evolves smoothly. When you measure, you become entangled with the system. The universe splits into branches. In one branch, you see outcome A. In another, you see outcome B. An analogy can help. Imagine you are watching a choose-your-own-adventure story. At each choice, the story could go left or right. In a normal book, you pick one path, and the other path stays on the page as unused ink. In many worlds, the book is not one book. It is a printing press that prints both versions, and you end up inside one printed copy. This is a strange picture, but it has one big advantage. It treats the quantum equations as universal. No special collapse. No vague boundary between quantum and classical. The cost is that it fills reality with branches we never see. Here is the next challenge. If many worlds is true, why do we experience a single outcome, not a blur of outcomes? The answer involves something called decoherence. Decoherence is the process by which quantum superpositions become effectively separated because they interact with the environment. In plain terms, the world is noisy. Particles constantly bump into each other. Information leaks out. That makes interference between different branches vanish extremely fast. A simple analogy is two radio stations. If you tune a radio and you can hear two stations at once, the signals are interfering. But if you put thick walls between the radio and one station, and you also jam the signal with noise, you stop hearing the mixture. You hear only one station. Decoherence is like walls and noise. It does not destroy the other station. It just makes it impossible to hear both at once. So in many worlds, branches become isolated. You experience one branch. Now, is this testable? This is where the debate becomes intense. Many worlds and other interpretations can make the same predictions for experiments we can do. That makes it hard to choose between them. Some people argue that because many worlds is mathematically simple, it should be preferred. Others argue that adding infinite branches is not simple at all. So many worlds is a kind of multiverse that may be real, but it is not obviously confirmable. We will keep building this slowly, and we will return to the question of evidence. For now, just hold one idea. When physicists talk about a multiverse, they are often not trying to add fantasy. They are trying to avoid an uncomfortable gap in an explanation. Sometimes the multiverse appears because a theory naturally produces many regions. Sometimes it appears because we do not know how to explain a number without selection effects. And sometimes it appears because we are tempted by the beauty of the idea. As the night continues, we will take each version of the multiverse and hold it up to the same light. We will ask what it clarifies, what it complicates, and what a careful person should believe right now. Let us slow down and go deeper into inflation, because this is one of the main places where many universes can appear without anyone trying to be dramatic. Inflation started as a solution to a few puzzles. One puzzle is called the horizon problem. When we look at the cosmic microwave background, we see that it has almost the same temperature in every direction. It is like looking at a bath that has the same warmth everywhere, even in corners that never touched. In the early universe, parts of the sky we see today were so far apart that, in a simple model, they could not have exchanged heat or information. So why do they look so similar? Inflation gives a simple answer. Those regions were once close together. They did have time to come to the same temperature. Then, inflation stretched space so fast that they became far apart. So today they look like two corners of a huge room, but long ago they were neighbors. Another puzzle is called the flatness problem. When we measure the geometry of the universe, it looks very close to flat. Flat does not mean it is a sheet of paper. It means that, on large scales, the rules of geometry behave like the geometry you learn in school. Parallel lines do not strongly curve toward each other or away from each other. In a simple, expanding universe, flatness is unstable. Even a tiny curve early on tends to grow into a big curve later. So a universe that stays close to flat needs very special starting conditions. Inflation makes flatness natural. If you zoom in on a sphere, the surface looks flatter and flatter. Inflation is like a massive zoom in. It takes any initial curve and stretches it until it looks almost perfectly flat. So inflation is not just a random idea. It was built to explain real features of the sky. But the details matter. Inflation is not one single model. It is a class of models. To describe it simply, imagine a hill and a ball. The ball represents a field, often called the inflaton field. A field is just something that has a value at every point in space. Temperature is a field. Air pressure is a field. The inflaton in these models has energy. The hill shape represents a kind of energy landscape. If the ball sits high on the hill, it has high potential energy. As it rolls down, that energy can drive a period of rapid expansion. In many models, inflation ends when the ball reaches the bottom of the hill. Then the energy gets converted into particles and radiation. That is like reheating the universe. Now here is where the multiverse can sneak in. In some models, the hill is not smooth and simple. It has plateaus. It has dips. It has places where the ball can get stuck for a while. It also has quantum noise, because everything in quantum physics has some jitter. So instead of one ball rolling down in the same way everywhere, you can get a patchwork. In one region of space, the ball rolls down and inflation ends. In another region, quantum noise kicks the ball back up a bit, so inflation continues. In another region, it gets delayed. If the regions where inflation continues expand faster than the regions where it ends, then the total volume of inflating space can keep growing forever. Inflation never ends everywhere. It ends in pockets. Those pockets are the bubbles. This is why people call it eternal inflation. It is important to notice what is being claimed here. This is not the claim that the laws of physics are made up and can be anything. It is the claim that one theory, when you push it, can lead to a process that creates many large regions that are effectively separate. So if inflation is correct, and if the eternal version is correct, then a multiverse is not a choice. It is a consequence. Now, what would count as evidence? The basic evidence for inflation is indirect. It comes from patterns in the cosmic microwave background. It comes from the way small density ripples would be stretched and frozen in. Those ripples later become the seeds of galaxies. The eternal inflation part is harder. One possible sign is a bubble collision. If two bubble universes formed near each other and their walls collided, it could leave a scar. That scar could show up as a ring or a strange cold spot in the cosmic microwave background. People have searched for this. It is a difficult task. The data is noisy. There are many ways to mistake a random pattern for a signal. So far, there is no clean, widely accepted sign of a bubble collision. Another possible sign is a specific pattern in the distribution of fluctuations. Inflation predicts a certain kind of pattern, almost, but not perfectly scale invariant. It also predicts that the fluctuations should be very close to Gaussian, meaning they follow a normal distribution. The better our measurements get, the more we can constrain inflation models. But even if we confirm inflation very strongly, we might still not be able to confirm the eternal part. This is one of the key themes of the multiverse. Some versions are connected to testable physics, but the other universes part can remain just beyond reach. This leads to something called the measure problem. The measure problem is what happens when you try to do probability in an infinite multiverse. If eternal inflation produces infinitely many bubbles, and some bubbles are like ours and some are not, how do you compute the chance of being in one type versus another? In normal life, probability is like drawing marbles from a bag. If a bag has 9 red marbles and 1 blue marble, the chance of red is 90%. But in an infinite multiverse, the bag has infinite marbles. It may have infinitely many red and infinitely many blue. If you try to compare infinity to infinity, you can get nonsense. It is like asking, which set is bigger, the set of all even numbers or the set of all integers? Both are infinite, yet you can pair each integer with one even number, showing they are the same size in a certain sense. But you can also get strange results depending on how you count. So the measure problem is a warning sign. It says, we do not yet know how to make clean predictions in some multiverse models. If a theory cannot tell you what is likely, it struggles to be tested. Now, this does not automatically kill the idea. It can mean our math tools are not ready. It can mean we are missing a deeper principle that selects a measure. But it shows that the multiverse is not an easy escape from hard questions. It can create new hard questions. At this point, it helps to step back and talk about what counts as a good explanation. In science, we often prefer explanations that do not multiply entities without need. This is often called Occam's razor. But Occam's razor is not a law. It is a guideline. Sometimes nature really is complicated. Sometimes a simple-looking explanation hides complexity. For example, the weather is caused by air moving is a simple sentence, but the weather is still extremely complex. So when someone says, the multiverse is too complicated, the right reply is not, so it is false. The right reply is, what does it explain that simpler ideas do not? Now we can connect this to fine-tuning. Fine-tuning is the idea that some parameters in physics seem to sit in a narrow range that allows complex structures. A simple analogy is a recipe. If you bake bread, the amount of yeast matters. Too little, the bread stays dense. Too much, it can overflow or taste strange. Life in a universe may be like bread in a kitchen. Some ingredients matter, but the analogy has limits. A recipe is chosen by a baker. The universe is not. So we use fine-tuning carefully. We treat it as a question, not an answer. Here are a few examples often discussed. One is the cosmological constant, sometimes called dark energy. Dark energy is the reason the expansion of the universe is accelerating. We can measure its effect. The puzzling part is that, in some theoretical calculations, you might expect the cosmological constant to be enormous, but the observed value is very small. If it were much larger, the universe might expand so fast that galaxies could not form. So people ask, why is it small but not zero? Another is the strength of gravity. If gravity were much stronger, stars might burn too fast or collapse too quickly. If it were much weaker, matter might never clump into stars. Another is the balance between forces that shape atomic nuclei. If that balance was different, elements like carbon might be rare. Now, there are two broad ways to approach these questions. One is to hope for a deeper theory that forces these values. In that case, there is no fine-tuning. There is just one consistent solution. The other is to accept that the values could vary, and then to explain our observed values through selection. That is where a multiverse can fit. If different regions of a multiverse have different constants, then we should not be surprised to find ourselves in a region that allows observers. Again, this is a selection effect, not a purpose. But here is the catch. Selection effects can explain why we see what we see, but they do not always explain why the deeper reality exists. It is like explaining why a fish lives in water by saying, fish can only live in water. That is true, but it does not explain why there is water. So even if anthropic reasoning is valid, it may feel like a partial answer. Now we come to string theory and the landscape. We will treat string theory gently. String theory is the idea that, at the smallest scales, the fundamental objects are not point particles, but tiny vibrating strings. Different vibrations correspond to different particles. The appeal is that string theory can include gravity naturally. But string theory also predicts extra dimensions. Not extra dimensions you can walk into, but dimensions that are curled up very small. The shape of those curled dimensions can affect the physics we see. So in many versions, there are many possible shapes. Each shape leads to a different effective set of laws. This creates a huge number of possible vacua. If that number is real, then our universe could be one choice among many. Combine this with eternal inflation, and you get a picture. The inflating space produces many bubble universes. Each bubble lands in a different vacuum. Each vacuum gives different constants. This can provide a framework where fine-tuning is not mysterious, but it comes with a high price. It is very hard to test. If we cannot access the other vacua, and if the theory allows too many possibilities, then it can become difficult to make unique predictions. This is why some critics say the multiverse turns physics into philosophy, and why some defenders say no, it is still physics, because it comes from the most serious attempts to unify our theories. The honest answer is that it is still an open debate. Now, as promised, we will return to the question, what could prove a multiverse wrong? For the large space multiverse, it is hard to prove wrong. It is more a consequence of infinite or very large space. For the inflationary multiverse, the strongest way to weaken it would be to rule out the types of inflation models that lead to eternal inflation. For the quantum many worlds multiverse, it is hard to prove wrong because it is an interpretation. But if we found a clear, precise, well-tested collapse mechanism that must be real, that would push against many worlds. For the string landscape, if string theory failed in key ways, or if it made predictions that were ruled out, that would reduce its force. But notice the pattern. It is not easy. So why do people still talk about it? Because the multiverse is one of the few ideas that can connect several mysteries at once. It connects the weirdness of quantum outcomes. It connects the early universe and inflation. It connects fine-tuning and anthropic selection. And it offers a frame where our universe is not the whole story. At the same time, we must be careful not to treat connection as proof. A story that ties everything together can still be wrong. So our job tonight is to keep that balance. We will continue slowly by taking each multiverse path and walking it to its end. We will see what kind of world it implies, what it demands we believe, and what it invites us to doubt. Now let us make the multiverse feel less like a word and more like a set of concrete ideas you can hold. Think of a city at night. From the ground, you see only the street you are on, the lights you pass, the buildings in your neighborhood. But the city has other neighborhoods. Some are close, some are far. Some have different rules and culture, but they are still part of the same city. Now imagine a stronger claim. Imagine there are other cities you cannot reach at all, not because they are far away on the map, but because the roads between cities do not connect. They are like separate game servers. In multiverse talk, the big universe idea is like other neighborhoods. The bubble universe idea is like separate cities. The many worlds idea is like the same city branching into many versions after every choice. The string landscape idea is like cities built with different building codes, different gravity, different chemistry. The important thing is that these are different claims. They sound similar in everyday language because we use one word, universe, for many things. In physics, the word can mean the observable region, or it can mean all of space and time, or it can mean one connected bubble, so we keep the map clear. Now, let us take the multiverse question and press on it with a simple tool. That tool is prediction. If an idea cannot help predict anything new, it may still be interesting, but it becomes hard to call it science in the usual sense. So we look for places where multiverse ideas touch observable facts. For the large space version, the touch point is the geometry and size of the universe. Is the universe flat? Is it infinite? We can measure curvature. We can measure how close to flat it is. So far, it looks very close to flat. That does not prove infinity, but it keeps infinity on the table. For the inflationary version, the touch point is the cosmic microwave background and the distribution of matter. Inflation models make predictions about the shape of the power spectrum, about the tilt, about how fluctuations behave. The data so far fits inflation fairly well, but there are still competing models. And the bubble part is harder. For many worlds, the touch point is quantum interference and decoherence. Many worlds is designed to match standard quantum predictions. It does not easily give you a new test. It mainly offers a different story for what the equations mean. For the string landscape, the touchpoint is string theory itself. Does string theory predict anything we can test? So far, it has struggled to do that cleanly. This is why the multiverse idea is not one thing. Some parts are supported, some parts are open, some parts are speculative. Now we can ask another question. If multiverse ideas are hard to test, why do serious physicists keep working on them? One answer is honest boredom with a missing piece. In physics, there are two deep frameworks that both work extremely well in their own domains. One is general relativity, which describes gravity and the large-scale structure of space and time. The other is quantum mechanics, which describes the small-scale behavior of particles and fields. Both are tested, both are useful, both are beautiful, but they do not fit together easily. When we try to unify them, we are forced into strange territory, and sometimes the multiverse appears as a side effect. So for some physicists, the multiverse is not a hobby. It is what falls out when you take the math seriously. Another answer is that some problems feel like they want a selection effect. The cosmological constant problem is one example. In simple terms, quantum fields contain energy. If you add up the energy contributions in the simplest way, you might get a huge vacuum energy. But the observed vacuum energy is tiny. So you either need a mechanism that cancels almost all of it with extreme precision, or you need a selection explanation. A multiverse can provide a selection explanation. If vacuum energy varies among regions, then observers appear only in regions where it is small enough for galaxies to form. This is not a proof. It is a way to make the number less surprising, but it changes the style of explanation. Instead of, this must be the value, you say, many values exist, and we find ourselves in one that allows us. Whether you accept that as science depends on your philosophy of what science should do. Now let us take a breath and do something important. Let us separate two emotional reactions people often have. One reaction is excitement. The multiverse feels like a bigger story. It feels like reality is deeper than we thought. The other reaction is anger. The multiverse can feel like an escape hatch. It can feel like a way to avoid doing the hard work of finding a more direct explanation. Both reactions can be understandable, but neither reaction is evidence. So we keep the calm, documentary voice. Now, if you want a clean way to think about how plausible a multiverse is, think about how many extra assumptions it adds. Here is a basic rule. If you already believe a certain theory for other reasons, and that theory implies a multiverse, then the multiverse comes along for the ride. If you do not believe the theory, then the multiverse does not get free points. So the question becomes, how strong is the underlying theory? Inflation is the strongest candidate here, because it was created to solve real puzzles, and it matches real data. But inflation itself is not fully proven, and eternal inflation is a stronger claim. Many worlds is similar. It is not invented to create many universes. It is invented to remove collapse. If you find collapse unacceptable, many worlds looks attractive. If you are fine with collapse, you do not need the branches. String landscape depends on string theory being on the right track. If string theory is not the right road, the landscape is not the right map. Now, let us talk about one of the cleverest objections to multiverse thinking. The objection is not, it sounds weird. The objection is about explanation itself. If the multiverse can explain anything, it can explain nothing. This is the fear. It is like having a detective story where the detective says the suspect could be anyone and any motive is possible, therefore the case is solved. That is not a solution. That is a surrender. So defenders of the multiverse try to show that it does not allow anything. They try to show that it has statistical structure. They try to show that it still makes constraints. For example, even if a multiverse contains many values of a constant, it may not contain all values equally. The distribution could matter, and the selection effects could matter. So some multiverse models attempt to make predictions in a probabilistic way, but the measure problem makes that difficult. So we are honest. This is still being worked out. Now, let us add another set of analogies, because these ideas become clearer when you see how selection effects work in everyday life. Imagine you are a person who wakes up in a room. The room has oxygen, a comfortable temperature, and drinkable water. You might be tempted to think the room was designed for you, but you could also consider another explanation. Maybe there are many rooms with many different conditions. You can only wake up in a room that allows you to wake up, so you should not be surprised to find oxygen. This is the anthropic logic. It is not mystical. It is like saying, every time I look, I find myself alive. Of course you do. Now the weakness of this logic is that it does not tell you how many rooms there are. It does not tell you what the distribution of rooms is. It does not tell you whether the room system exists for some deeper reason. So it is a piece of reasoning, not a full story. Now we can ask a question that is both simple and deep. If a multiverse exists, does it matter for your life? In a practical daily sense, not much. The stars still burn. Gravity still holds. You still live in this branch, in this bubble, in this sky. But philosophically, it changes how you think about uniqueness. It changes how you think about chance. It changes how you think about meaning. Some people fear it because it makes them feel small. Some people love it because it makes reality feel richer. But again, those are feelings. Science asks what is true. Now we can return to many worlds and make it more grounded. Many worlds is often described with dramatic examples. In another universe, you became a different person. That is a poetic way to say it. But the core idea is much more technical. It is about whether the wave function is the whole story. If it is, then the wave function evolves deterministically. And splitting is not a magical event. It is a natural result of entanglement. Entanglement means that two systems become linked so that you cannot describe one without describing the other. When a measuring device interacts with a quantum system, they become entangled. Then, the combined system contains multiple correlated outcomes. Each outcome includes a version of the device showing that outcome, and a version of the observer seeing that outcome. That is the branching. Now, why do we not feel the branching? Because of decoherence. Because the environment is always interacting. Because information leaks out and the branches stop interfering. So from inside one branch, the other branches are like pages you can never turn to. They are not nothing. They are just unreachable. Now there is a clever question people ask. If many worlds is true, why do we talk about probability at all? If all outcomes happen, what does probability mean? Many worlds has answers. Some are based on decision theory. Some are based on measures of branch weight. But these answers are still debated. So even within many worlds, there are unfinished parts. Now we can summarize the honest state of the multiverse idea. Some versions are almost trivial consequences of large space. Some versions are plausible consequences of inflation. Some versions are interpretations of quantum mechanics. Some versions depend on speculative high-energy theory. None of these is yet a settled fact. So if you are a careful person, what do you believe right now? A careful person can say this. It is very likely that the universe is larger than what we can observe. It is plausible that inflation happened. It is uncertain whether eternal inflation is real. It is uncertain which interpretation of quantum mechanics is correct. It is uncertain whether string theory describes reality. And it is uncertain whether any multiverse exists in a strong sense. Now this sounds like a lot of uncertainty, but that is normal in frontier science. The edge of knowledge is not a clean line. It is a foggy shoreline. Some rocks are solid, some are hidden. Some are just waves that look like rocks. So our job is to move slowly and not pretend. In the final part of this episode, we will do two things. We will collect the strongest arguments for multiverse thinking in one place, and we will collect the strongest reasons to resist it in one place. Then we will end the night with a simple idea. Whether or not a multiverse exists, the universe we do live in is already astonishing. It is a place where matter can think. It is a place where stars can build the atoms that become blood and bone. It is a place where math can describe the sky. And even if there are many worlds, this one is still the one you are in. So let us gather the strongest reasons people take the multiverse seriously. Reason 1 is mathematical honesty. If a theory you already trust implies many regions or many outcomes, it can feel dishonest to pretend those extra parts do not exist just because you cannot see them. This is the many worlds motivation in a nutshell. It says, the quantum equations are simple and universal. If we stop adding special rules for measurement, then branching is what you get. And if branching is what you get, then the multiverse is not a fantasy. It is a description of what the math is doing. Reason 2 is cosmic plausibility. Inflation, in one form or another, is a strong candidate for what happened in the early universe. If inflation happened, then the next question is what kind? And if the most natural kind in the space of models is an eternal kind, then bubble universes appear as a physical process, not as a poem, as a process like snowflakes forming in a cloud. Reason 3 is explanatory pressure. Some numbers in physics look like they are begging for a deeper explanation. Maybe there is a hidden symmetry that forces them. Maybe there is a dynamical mechanism that sets them. But if, after decades, we still have no clean mechanism, some physicists become willing to consider that the numbers are not unique. They might vary. And if they vary, then selection effects become relevant. A multiverse can turn a mystery into a selection story. This does not prove it is true, but it makes it attractive. Reason 4 is humility about our position. Human beings have a long history of thinking their local region is the whole story. The village is the world. The continent is the world. The planet is the world. The solar system is the world. Then we learn the local region is one small piece in a much larger structure. So some people see the multiverse as the next step in that pattern. It might be true, or it might be a false pattern. but the pattern makes it emotionally plausible. Now, the strongest reasons to resist the multiverse. Objection 1 is testability. A scientific claim needs some path, even indirect, toward being checked. If other universes are forever hidden, the claim can drift away from experiment. It becomes more like metaphysics. Now, metaphysics is not useless. It can still be about reality, but it is not the same as laboratory science. So critics worry the multiverse blurs the boundary. Objection 2 is the measure problem. If your multiverse is infinite, you need a way to say what is typical. Without that, you cannot do clean prediction. If you cannot do prediction, you cannot do strong confirmation. Objection 3 is the danger of lazy explanation. If you can explain any constant by saying, it takes many values somewhere, then you might stop looking for deeper structure. This is a real fear. It is like giving up on understanding a machine because you can always say, in some version of the machine, the dial is different. That may be true, but it may also be a failure to ask the right question. Objection 4 is that the multiverse can be unfalsifiable in practice. A theory can be falsifiable on paper, but not in the real world. For example, you could say, if we could travel faster than light, we could check the other bubble. But we cannot. So the question becomes practical. Can any realistic observation push the idea up or down? Now, a careful person can hold both sides. You can accept that the multiverse is not confirmed. You can also accept that it might be the least bad explanation in some contexts. This is the mature stance, not certainty, not mockery, calm, provisional belief. Now, to keep things clear, let us use one more analogy. Imagine you are trying to understand a huge computer simulation. You live inside it. You can observe the rules. You can measure constants, but you cannot see the outside computer. Now, someone suggests that the simulation might be running many instances. In one instance, the settings are slightly different. In another, the random seed is different. In another, a patch was applied. If you cannot see the outside machine, can you ever know? Maybe not directly, but you might infer it if you see patterns that suggest selection. For example, you might find that your settings are near the edge of stability, not too stable, not too unstable, just stable enough to form complex structures. That could be a hint, not a proof, that settings were varied and many runs failed. This is what anthropic reasoning tries to do. It tries to treat the universe like a system that could have many settings. Now, the danger is that this kind of inference can become circular. You can always say, we observe this because otherwise we would not observe. True. So the real challenge is to find independent constraints, a distribution of settings that comes from theory, a measure that comes from theory, a prediction that comes from theory. Without those, the multiverse becomes a story you can never tighten. Now, let us return to the audience point. Layman terms, 20 years old. If you are 20, you have lived in a world where many things seem to branch. Your life has choices. Your feeds show different timelines. Your games have different paths. So many worlds can feel like a cosmic version of this. But the real content is not about your choices. It is about whether quantum outcomes are unique, and whether a universal wave function is the right description. So we keep it grounded. If you flip a coin, you see one result: heads, tails. In classical thinking, the other outcome did not happen. In many worlds thinking, both happened, but you are in the branch where you saw one. Now, you should not treat this as a fact. Treat it as an interpretation. Now, inflationary bubbles. If you are 20, you have seen soap bubbles. They form, they expand, they separate. Sometimes they collide, sometimes they pop. So bubble universes are not hard to picture. But again, you should not treat the picture as proof. The question is whether the physics of the early universe has the same pattern, and whether any signature could reach us. Now, one last theme. The multiverse debate is also a debate about what a good scientific explanation should feel like. Some people want the universe to be like a solved puzzle. They want a unique answer, a final theory where everything is forced. Other people are comfortable with a universe that contains variation. They are comfortable with statistical explanation, not because they want it, but because many parts of science already work that way. We do not predict the exact path of every molecule in a room. We predict temperature and pressure. We do not predict the exact life of every individual. We predict population trends. So a multiverse could be the ultimate statistical system. But again, statistics needs a measure, so we keep returning to that. Now we come to the slow end. If you remember the library at the start, we can return to it. Maybe there are many shelves. Maybe there are many rooms. Maybe there are many libraries. Maybe there is only one book. What matters tonight is not that you pick the most exciting option. What matters is that you understand the options clearly. So if someone tells you the multiverse is proven, you will know to ask, proven how? If someone tells you the multiverse is nonsense, you will know to ask, nonsense compared to what alternative? And if someone tells you we do not know, you will recognize that as a normal, honest place to stand. Now let your breathing slow. Let the ideas become soft. The multiverse, in the end, is a way of asking how big reality might be. Whether it is one universe or many, the night sky remains the same. A calm spread of light, a quiet pattern of distance, a deep, patient silence. And in that silence, you can feel this simple truth. We are here. We are thinking. We are looking out. And that alone is already strange and beautiful. Before we fully let go of the topic, let us leave you with a simple set of mental tools, not to argue online, not to win a debate, just to keep your mind clear when you hear multiverse claims. Tool 1 is the level question. Ask, what level are we talking about? Are we talking about regions beyond the observable horizon in the same universe? Are we talking about inflationary bubble universes? Are we talking about many worlds branches? Are we talking about a landscape of different physical laws? If someone cannot answer this, they may be using the word multiverse as a mood, not as an idea. Tool 2 is the evidence question. Ask, what observation does this idea help explain better than the alternatives? If the answer is fine-tuning, ask which constant and why. If the answer is quantum randomness, ask what problem it solves compared to collapse. If the answer is inflation, ask which inflation model and what signatures it predicts. Tool 3 is the falsification question. Ask, what would change your mind? This is not a trap. It is a measure of seriousness. A person can say, I do not know what would falsify it right now. That can be honest. But if a person says, nothing could falsify it, and I am certain anyway, that is a warning sign. Tool 4 is the humility question. Ask, are we treating a gap in knowledge as a gap in reality? Sometimes we do not know why a number has its value, because we do not yet have the deeper theory. In that case, the multiverse might be unnecessary. Other times, the math we do have genuinely suggests that many outcomes exist. In that case, the multiverse might be the simplest description. The honest position can shift as science improves. Now we can add one more analogy to make the mood softer. Imagine you are standing on a beach at night. The ocean is dark. You cannot see the far edge. You cannot even see most of the waves, but you can hear them. You can feel the air. You can measure the tide. From those small measurements, you infer a larger reality. That is what good science does. It does not require you to see everything. It requires you to infer carefully from what you can see. The multiverse question is, in a sense, a question about how far inference can go. How much unseen structure is reasonable to infer? At what point does inference become storytelling? Different physicists draw that line in different places. That is why the debate can be intense. But the debate is not hopeless. It is part of how science grows. Over time, theories that fail to connect with reality weaken. Theories that make sharp predictions strengthen. The fog clears slowly. Now, if you want a grounded takeaway, it can be this. Right now, there is no single experiment that proves a multiverse. There is also no single argument that fully kills it. It is a possibility that sits on top of real physics and real unknowns. A reasonable person can stay curious. A reasonable person can stay cautious. A reasonable person can say, "I do not know," without feeling embarrassed. And a reasonable person can still enjoy the beauty of the question, because the question is not only about many universes, it is about what it means for one universe to be understandable. It is about whether reality is one clean equation, or a branching forest of outcomes, or a landscape of different rules. And if you have made it this far into the night, you have already done the most important thing. You have kept your attention on a difficult idea without turning it into a slogan. Now, let the idea become quiet. Let it drift like mist across a dark field. Let it settle into the background like a steady rain. And let sleep take over, one slow breath at a time. If your mind is still turning, it can help to remember that uncertainty is not the same as emptiness. In everyday life, you accept invisible things all the time. You accept that there are cities you have never visited. You accept that your body has cells you have never seen. You accept that radio waves pass through the air, even though you cannot touch them. You accept these, not because someone told you a story, but because the evidence connects. The multiverse is still trying to earn that kind of connection. Some parts of the multiverse idea are already connected to evidence, like the way inflation models fit the sky. Other parts are more like a sketch on the edge of a page, waiting for a sharper test. So you do not need to force a conclusion. You can keep the idea in a safe container in your mind, labeled possible. And you can let that be enough for now. Curiosity does not require certainty. You can enjoy the puzzle without forcing it to end. You can notice which parts of the story are strong and which parts are still waiting. And you can remember that the best scientific attitude is often patient, not dramatic. It is slow attention. It is careful language. It is the willingness to say, "I might be wrong." And it is the discipline to wait for the next piece of data. If your mind is still turning, give it one last simple image. Picture a single candle in a large dark room. The candle is your current understanding. It lights up a circle of floor around you. You can study what is inside the circle. You can describe it clearly. You can measure it. You can even use it to make predictions about what might be just outside the circle, like guessing there is a wall, because the air feels cooler in one direction. But you cannot skip ahead and pretend the whole room is already mapped. Outside that circle, there may be more furniture, more doors, more hallways, maybe even other rooms. The fact that you cannot see them does not mean they are not there, but it also does not mean you should claim to know exactly what they contain. You can be honest about the light you have. You can be honest about the darkness beyond, and you can keep walking slowly as the circle of light expands. That is how knowledge grows. And when you hear big claims, you can use that candle rule. Ask what is lit by evidence. Ask what is still in shadow. Ask which parts are supported by measurements and which parts are supported mainly by taste, by preference, or by hope. You do not need to attack the shadow, and you do not need to worship it. You can simply notice it and keep the candle steady. And it is also how a person stays calm in the face of big ideas. This was a quiet archive story, where the story ends, sleep begins,